Hi, everyone. Can you all see the whiteboard? Okay. What answers did you get for the first question? Good. 3542 is right. Okay, Sanvi, can you explain?
Okay, so it says that the numbers the 4 digits add up to 14, and if the two middle digits are 9, that means the remaining 2 digits, the thousands and the ones place, that means they're equal to 5. And so it says the thousands digit minus the units digit is 1. So the only numbers that would fit that are 3 and 2, because if you do 3 plus 2, it equals 5. And 3 minus 2 is 1. So if 3 goes in the thousands place, and 2 goes in the ones place. And it also says that it's divisible by 11. So if 3 is the first number, then you know the second number is greater than 3. And then the third number, or the tens place, will be greater than 2. So it says that these two missing digits, they equal 9. So if you already have a 3 and a 2 there, 5's 5 are taken, so that means there's 4 more, and the only 11 the multiple of 11 that which their digits add up to 4 is 22. So you just add 22 to that, and it becomes 3542.
Good. Yep. So that's correct, and that gives us 3542. So one thing to maybe make the last step a little bit easier. So does anyone know of an easy way to check divisibility by 11? Okay, so the trick is you can add up the digits in the even positions and odd positions. So basically you can do like here A plus A minus B plus C minus D here, and this should be a multiple of 11, could be negative. So it could be negative 11 and so on. So in general, you can take the digits of a number and you can look at the odd. So in general, you could take the first digit, third digit, fifth digit, and so on, add those up and subtract the second digit, fourth digit, sixth digit, and so on. You add those up and subtract. But that's the same as saying the first one minus second plus third minus fourth and so on. So this needs to be a multiple of 11. It could also be 0 or it could be negative. So let's look at what that is here. So A minus B plus C minus D, what do we get here? So 3 minus 5 plus 4 minus 2, we get 0, right? So that's a multiple of 11. That's 11 times 0. So in this case, once we get, like Sanvi said, we can get the first and last digit pretty easily because we know that the sum of the digits of the middle digits is 9, and all 4 digits add up to 14. So first and last is 5, and we know the difference is 1, so that we can get easily as 3 and 2. The middle 2 digits we have to actually check for multiples of 11, right? So to make that a little bit easier, if we know this should be a multiple of 11, we can first try, okay, this should be 0. So then we know what B minus C should be. That difference should be the same as A minus D. That should be 1. And then knowing that their sum is 9, we can just try 5, 4 there and see that this gives us a multiple of 11 and fits all the criteria here. Does this make sense? Any questions? Okay, let's move on to the next question. What were your answers for this question? Okay, good. 35 is correct. Preeti, can you explain?
Okay, so there was three combinations to do it. So 4 6s plus 3, 3 6s plus 5 plus 4, and 2 6s plus 5 plus 5 plus 5. So for each separate combination, you can find how many combinations are in that one by doing the number of terms factorial over the number of times each one occurs factorial. So for the first one, it would be 5 factorial over 4 factorial, and then you would get 5. For the next one, you would do 5 factorial over 3 factorial and get 20. And then for the last one, you do 5 factorial over 2 factorial times 3 factorial. And you would get 10. So when you add them all up, you get 35.
Good. This should actually be
1.
Yeah. That's just that. Yep. Good. Okay, so this works and this counts the correct numbers. So I guess on one way, so one thing you could do here is for each of these, you could look, as Preeti said, you can take the number of total items that you want to shuffle. So we basically want the number of orderings. We know that 4 dice should say 6s and 1 dice should say 3. How many orderings of that are there? So one way of doing this is to say, okay, there's 5 factorial orderings of all of these, and divided by 4 factorial because these 4 6s are the same. So we don't want to count the repetitions of those or the orderings of those 4. And same here. For the ones which are the same, we have to divide by that factorial. So here there's 2 6s and 3 5s. So we divide by 2 factorial times 3 factorial. Another way to do the same kind of counting is, so here we have 4 6s and 1 3. So basically we just want to choose, of the 5-digit locations, we want to just choose one of them for the 3. So there's 5 choices for that. That makes sense. For the second one, we want 3 6s, 1 5, and 1 4. So we could just choose one of 5 locations to put the 5. So which die roll should have gotten a 5, and 4 choices for where the 4 should have come. So 5 times 4 is 20 for the number of ways for this set of dice. And then for the last one, 2 6s and 3 5s, we want to just choose the locations for 6s. So 5 choices for the first 6, 4 choices for the second 6, but it doesn't matter which order we pick them. So 5 times 4 times divided by 2 is the same 10 here. So it's the same counting. We could do it in a different way. So both of these ways will give us a total of 35. Now there's one more way we could do this problem, and this is using the stars and bars or ball and urns method that I think we had gone over a few classes ago. Does anyone remember that method? Any ideas of how you can apply that here? So let's just remember the idea, which was, if I think we had talked about it with a donut problem. So if you have some number of items, you want to put dividers in between to say how many should be in different groups. So for instance, if I have 6 items and I want to put them in 3 groups. So I think one example is 6 donuts, and I want to say some that I buy will be glazed, some will be chocolate, some will be strawberry. So I can decide, okay, I put 1 divider here, 1 divider here. That means the first one is chocolate, first one is glazed, 3 are chocolate, 2 are strawberry. And based on where I put the dividers, that uniquely determines a combination for how many of each kind that I get. So then I could just count the number of ways that I could put the dividers here. That was a summary of the method that we saw before. Now let's think about it, how that would work here. So we could kind of structure this as, imagine if I had 27 dots here. Now, basically, if I snake 5 dice, I could say, okay, I'm putting 4 dividers. 1 here, and so on. And say that, okay, the number of dots before the first divider is the roll that I get on the first die. Between the first and second is how many I get on the second die roll, and so on. So would this method directly work? Any ideas? Why or why not? So think about a case, if I have 27 dots, I could put my first divider after 19 dots. Let's say there were 19 dots before this point. That means that my first roll had to have gotten 19, and then I'm dividing the remaining 27 by the in the other dice, right? So the problem here is it's not actually keeping track of that. The maximum I can actually put in one roll is 6, right? And when I just say, where do I put the dividers, I don't actually account for that extra issue. So we can actually think of a small variant of this, where we actually will count, instead of the number of ways to spread out the 27 among the 5 dice, let's think about spreading out the extra. So what is the maximum I could get in these 5 rolls? So a maximum I could get 6 on each roll times 5, so a total of 30. So I want to get an outcome of 27. So basically there's just an extra of 3. So basically I have to say, I have to spread out 3, like losing 3 from the maximum among my die rolls. So I could lose 1 from the first, that means rolling a 5 the first time, and losing 2 from the last one. So that corresponds to getting a 4 on the last roll. So effectively, this problem would then be equivalent to saying, if I had 3 dots, that's my 3 extra rolls, I want to spread those out between the 5 die rolls. So that means there's 4 dividers. So if I think about an example like this, I would say there's no dots before the first divider, so first roll will be a 6. Second roll here, there's 3 dots here, so this is a 3. No dots here, 6. No dots here, 6. No dots here, 6. So that's corresponding to 6, 3, 6, 6, 6. So that's one of the combinations. So now basically we want to say we have 3 dots and 4 dividers. So how many ways are there to position these is equivalent to the answer to the whole question. So that's the same thing that we could do, either what Preeti suggested with the same way of counting these, 7 factorial divided by 4 factorial times 3 factorial. Or you could just do, of these 7 items or 7 places to put either a ball or a divider, I can choose the 3 places to put the balls or the dots that I want to remove. So 7 choose 3 is 7 times 6 times 5 divided by 3 factorial, which is 35. So we can get the same answer a little bit easier without actually having to count these separate cases. If we just think about what is the extra that we're kind of losing from the maximum. So there's no issue of having too many in one group, right? Because we can have all 3 in one, this just corresponds to a 3. If we had 10 dots here, that would be a problem because we can't actually have a -4 on one die. But here with 3, we could either lose 1, 2, or 3 on any of these die rolls. So this actually counts the same value, that we have 35 corresponding to the sum of these 3 numbers here. Any questions on this? Okay, so if you forgot this technique, you can look up either stars and bars, or sometimes called ball and arms. This is the method we had gone over with the donut problems, and this is also useful in questions like this. Okay, any other questions? Okay, let's move on to the last question. What answers did you get for this question? So I see a few answers of 24. So it definitely has to be at least 24. So let's see why that should be the case. Let's take 25 by 27. So you can divide, we have 4 by 6 note cards. So we could put, if you imagine putting 1 by 1 in this way, 1 and so on. So we know we can fit 6 note cards. Let's say the 4-dimension. So this we put 27, 6, the 6th dimension along the 27. So we can do up to 4 cards this way. And then in the other direction, we're putting 4, dimension of 4. So 25 over 4. We can do 6 cards. So if we kind of arrange them as a grid, as shown here, assume there's no spacing or as little spacing. I've just put spacing to make it easier to draw. So we know we can make 4 cards by 6 cards a grid, and we can make 24 cards. Okay, so we know that the minimum possible answer is 24 cards, but maybe there's a way of arranging it better. We don't have to put them in a grid, right? We could instead maybe have one that's like this with 6 by 4 this way, and some which are like this, right? 4 by 6 this way. So we don't know that this is necessarily the best answer we could get. Now on the other side, let's try to see what the maximum that we could get is. So I think Bharat has an answer of 28. Okay, how did you get 28? Bharat, are you muted? Okay, so let's think about what the maximum could be. The maximum could be if we think about the total area, 25 times 27, and divided by 4 times 6. So if we think about the total area, we know that each of the cards has to be an area of 24. So what is this value?
28.
28, good. So approximately 28. Okay, so this means that our answer, we know the minimum possible answer is 24. If we just put a grid, we know we can put 24 of these squares. The maximum is about 28. That doesn't mean we could actually get 28. We have to think about, okay, is there a way to actually arrange things in this way? Okay, so now let's try to think about what how we can actually arrange this. So let me erase this drawing. And let's think about what's the most efficient kind of packing of these that we can think of. So let's think about So 25 by 27. So let's think about what the wastage was when we were packing with just a grid. So when we put 6 in this dimension, 6 and then 6 and again, we were wasting the last 3 units, right? Because we could only use up 24 putting 4 cards this way, and we were wasting the last 3. So is there a way to use up more of this space? So let's think about that. So maybe let's do, so what combination of 4 and 6s could use up more of the 27 than just 6 times 4? Any ideas?
Five fours and 1 6.
Good, good. Yep. So that's one way we could do that. So let's try that. Let's put 1 6. Now we could put 5 4s. Okay, sorry, they don't look exactly the same, but these 4 are, let's just say they're the same size. These are all 4. So now how much did we take up? So I needed to fit one more. Let's assume there was one more there. Okay, so we have 5 4s and 1 6. So now we took up 26 of this, which is much better, right? So instead of wasting 3 units, now we only have to waste 1 unit. Okay, so now let's think about how many we can do coming down here. So this is 6 by 4. We can now take, how many times can this tile repeat here?
6.
6 times, good. So we have 6 tiles in this column, or 6 cards. What about for each of these 5?
4.
4, good. So 4 for this, and so on. So for the remaining, I have 4 times 5, which is 20 cards. So what am I getting total here?
$26 cards.
Good, 26 cards. So this is better, right? The first answer we had was 24. Now by arranging it in this way, we get 26. Okay, so the answer is actually this 26. Now we can think about the last kind of the challenge extension is, okay, can we show that 26 is actually the best? So just from this layout, we don't know, maybe there was some way we could have arranged it. So now we can't just do a 6 and some 4s. Maybe if we had moved some places 6s, some places 4s with different orientations, maybe we could have less wastage and actually fit more than 26 cards. So we know that the absolute maximum is 28. Maybe 27 or 28 is possible. So there's a way of showing that this is actually not possible. Are there any ideas for how you might show this? Okay, so one hint is that this number and this number are both even. Any ideas from that?
Since the 27 and the 25 are odd, there's no way that the 2 even numbers will go into them without any wastage.
Good, exactly, yeah. So the essentially, however I put 4s and 6s, right? If I think about any row, if I just draw a straight line through this or straight line this way, if I think about, okay, some places I'll have 6s, some places I'll have 4s, but if I add them all up, at every line, there will be at least 1 unit of wastage, right? Because there's no way that when I add up those even numbers, I can't get an odd number, right? So I'll always have 1 unit of wastage like as a row and 1 unit of wastage as a column. So effectively, this 25 by 27 is actually useless. Like all I actually have access to is the even portion of that. A 24-inch by 26-inch sheet is what I have access to. The extra 1 inch is not really useful because I don't actually have, I can't create an odd total in any place. I only can create an even total. So the maximum I can really use horizontally or vertically is 24 and 26. So if I think about that, what is the total area if I had a 24 by 26 sheet? Is 24 times 26, and now I can divide by 4 times 6, which is the area of each one. And what do I get here?
26.
26. Good. So actually, if I had a 24 by 26 sheet, that's the maximum I can do 26. And we just saw how we can actually use that. So if you look at what we did here, we're actually tiling exactly a 26 by 24 grid, and that extra one unit is wasted. So the maximum that we could do is actually 26 cards. Okay, any questions on this? Does this make sense? Okay, then
The solution makes it so easy. We don't have to like try to fit in, visually try to fit in the cards.
yeah, it does when you look at it this way. But yeah, I think you need to first kind of position it to think of this idea that you can actually use the one extra unit. Any other questions? Okay, that's it for today's class. We'll see you all next week.
Okay, thank you, everyone. We'll see you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.